Okay, our next speaker is ready to go. Alisa?
This one is really okay.
Okay.
Okay. Thank you very much for inviting me here, and thank you, Melvin, for organizing this conference and having me here multiple times. It's been a while since I'm here in person, so it's nice. So I'm going to talk about Euler-Kronecker constructs of maximal real cyclotomic subfields. And let me first give you the references, because I tend, when I give slides presentation, I tend to forget about the references because they're usually at the end. So I decided to begin with it. So this work, so how do I indicate? Okay, I do indicate it here, but you don't like it because then the Zoom speakers will not. Okay. So this work is based, this talk is based on two works, and one of them is about appearing math computations, and another one is published like a few years back. So, and I'm going to emphasize which are the results, which are our results, but there is like a big intersection on the topics, so just convenient to first introduce the notations. So we are going to have a few algebraic definitions, but since I'm doing analytic number theory, they will be just technical, and then once we go through, everything will become pretty analytical. So let K be a number field, and we call A its ring of integers, and that's a complex variable. And when the real part of S is greater than 1, we define the Dedekind zeta function as the following expression. And as you can see, so maybe I can do it over here. This is supposed to be visible. So, and just a sanity check, if we take K to be the rational numbers, then we get our normal Riemann zeta function, and then here we get sum over n from 1 to infinity, 1 divided by n to the s, and here we get 1 minus 1 over p to the s to the power minus 1. So everything is just fine, and this formula is nothing else than the Euler product formula. So, and in the same way, so this is the sanity check, and in the same way as the normal zeta function, Dedekind zeta function can be analytically continued to the whole complex plane except a simple pole at s equals 1. Okay, so now similarly to the normal zeta function, the Dedekind zeta function has Laurent expansion around s equals 1, and it gives you a constant alpha k divided by s minus 1 plus another constant c sub k plus some other constants times s minus 1, and so on and so forth. So what happens is that these constants, they are called still Ts constants, and we are interested in how alpha k and ck are related. So alpha k is a positive real number that carries some arithmetic information about k. This is why it is interesting, and the Euler-Kronecker constant is defined as gamma sub k sub the field, which is ck divided by alpha k. And again, the sanity check, if we are over the rationals, then here we have sum over n of 1 over n to the s, and here we have 1 divided by s minus 1 plus normal gamma, which is the Euler constant. So our gamma sub q is going to be equal to the normal Euler gamma. Okay. So, and then similarly to the normal Euler gamma, how it is defined, following the same procedures, we can get the similar expression for Euler-Kronecker constant. First, as a limit of 1 over alpha k. We don't see it in the normal case because it is just 1. And then this guy minus log x. And similarly, we can express it through the norm of prime ideals. Again, similarly, we will have here log p divided by p minus 1 in case of rational numbers. So just to keep track of the things, if we have many prime ideals that have small norm, then this implies that my gamma k is going to be small. Just to understand what is going on. And another equivalent definition that is going to be a lot more convenient for us is gamma k as the limit as s approaches 1 from the right as of the logarithmic derivative of zeta sub k plus 1 over s minus 1. Again, the same things happens for the normal Riemann zeta function. Why this is convenient? Because this thing, once I have the logarithmic derivative, I can write a Dirichlet series, and I can try to employ some complex analytic tools, and I can try to formulate something which is analogous of the prime number theorem. So this is how the tools usually originate. So, okay, what do you
close that?
This one?
Yes.
Worked. Okay, thank you. Yes. So in 2023, Dixit and Murgy did exactly that. So they considered an analog of von Mangold function, lambda sub k, that is defined via as a coefficients of the Dirichlet series of the logarithmic derivative of zeta sub k. And then we are going to get that 1 minus Euler-Kronecker lambda is equal to the same like expression as for normal lambda, as the integral from 1 to infinity of the sum of this generalized von Mangold minus the main term dx over x squared. So this means that Euler-Kronecker constant is directly like tied to the error term in the prime ideal theorem, which is an analog of prime number theorem. Okay, so, and the question is, like, one of the possible questions that you may ask is, like, how this gamma k, how they can behave depending on, like, k. So, and under GRH, for Dedekind zeta functions, there are absolute constants such that gamma k is squeezed between minus C1 log dk and C2 log dk, where dk is the absolute value of the discriminant. So this was studied by Hara in 2006, and this is just to keep track of what is going on. So here we have minus log, here we have a double log. So I'm going to refer to the average results later, but this is what we have under GRH. So, and now let's consider some particular cases because, you know, we have general K, and let's just consider some particular families that are probably more of arithmetic interest for us. So in case when Q is a knot prime, we define by zeta Q, there is a small collapse that typically happens in this literature. So zeta sub Q is not a zeta function. This is the root of unity. So this is Q's root of unity. And then if we adjoin it to Q and write K to be Q adjoint zeta Q, then this is a prime cyclotomic field. And we define gamma sub Q as gamma attached to this prime cyclotomic field, just for simplicity. And gamma Q plus is attached to Q plus of zeta of Q, where Q plus is the one when we attached zeta of Q plus zeta of Q inverse. Okay, and this we call maximal real cyclotomic field. These things are going to appear later, so better memorize them. And from now on, again, Q is going to be a knot prime. Just a little bit of disclaimer, if Q is not a prime, well, first of all, if Q is even, then things are boring and slightly more different. So you can just consider Q being even like separately, because this is only a very special case. When Q is not a prime, you can make a prime power and the same things are going to be working likely, but it's going to be very, very ugly. So that's why we are just assuming that Q is a knot prime. Okay, so zeta sub Q is the Q's root of unity, and Q of zeta Q plus is the maximal real cyclotomic field. So then what happens is that the zeta function splits into normal zeta and the product over L functions over all the characters that are different from chi0. And if we consider the zeta function attached to the zeta to the Q of zeta Q plus, then we get again the zeta factor, and then we get the product over all L functions such that chi of minus 1 is equal to 1. So, and this means that if we take the logarithmic differentiation and we try to get like what would be the expression for my gamma Q and gamma Q plus, so then we get gamma factor that will come from here, and then we'll get the sum over the logarithmic derivative of L, here just the full sum over chi different from chi0, and here the sum over chi of minus 1 equals 1. So, and this means that first of all, if we subtract one from another, gamma cancels out, and here we get only the sum over specific half of the characters, right? And if we take the ratio, again, if we take the ratio of these things, then zeta is going to cancel out, and then we are going to get something like this, which is the limit as s approaches 1 from the right of these zeta functions. So these two objects, they are pretty related, as we can see from this slide. And we are going to see more of how they are related later. Okay, so now the connection to the class number. It is just, you know, to give you an idea that this appears somewhere else. So let's denote H1 of Q be the ratio of the class number of Q adjoint zeta of Q and the class number H plus of Q plus, the maximal real subfield. So then what we are interested in the behavior of couple of Q, which is the normalized difference of Euler-Kronecker constants, normalized by log Q, and R of Q, which is logarithm of my capital R of Q. And my R of Q is actually related to this H1. So from the expression from before in here, so here is the difference of gamma plus minus gamma. So this is the sum of logarithmic derivative of L. And this is R of Q, which is the product of the values of L at 1. So, and what happens is that I normalize this by log Q. Why? Because there are heuristic arguments that tell you that this is the right normalization. And this guy is going to be related to the class number. So there is a way to compute it. Once you know something about it, there is a way to compute it using class numbers too. Okay. So then local expansion at s equals 1 gives you that the ratio of the zeta function is equal to R of Q times this factor, and it means that my R of Q is actually the value at s equals 1, and this guy, the difference of gamma, is the slope of the same function, essentially. And Kummer in 1851, so I had to put the full year here because otherwise it's not obvious which year I'm in, conjectured that R of Q is little o of 1, and it was later conjectured, like a lot later in 2015 or something around that, that kappa of Q is little o of 1 as well. And the natural question, once you look a little bit closer to these objects, is whether R of Q and kappa of Q actually are behaving exactly in the same way. And I'm not going to talk about it much. I can just tell you that we did some numerical computations, and it seems that they do in the terms that, you know, even the spikes that you get for R of Q and for kappa of Q, they have the spikes at the same location. So it's just numerics, but it's just good to know that at least when you have some extremal behavior of one function, you get extremal behavior of another one as well. Okay. So, and what we can know under GRH for our gamma Q now. So under GRH for the Dedekind zeta function, we have that gamma Q is bounded by log Q square, and then it was improved to log Q log Q. Of course, in analytic number theory, we cannot get a talk without multiple logs. And let me just, for simplicity, assume that P star of Q denotes the number of primes in the dyadic interval, so between Q and Q over 2 and Q. And then Kumar-Murty unconditionally proved that if we sum the absolute value of gamma Q over this dyadic interval, then we get P star of Q times log Q. So this is like roughly Q, right, with a constant, but it's more convenient to write it this way. So, and our first result from an earlier paper, our first result tells that you can do the same for gamma Q plus with the absolute value, and you can do the same for RQ. For RQ in absolute value, you get P star of Q, and if you assume something, this is really related to the distribution of primes in the proof. So if you assume a strong form of Elliott-Halberstam conjecture, meaning that you are really very, very uniformly distributed up to large moduli, then the upper bound here can be improved a little bit. To the little o, and here to the little o of P star of Q, as Q tends to infinity. So by GRH, we have that gamma Q plus, not an absolute value, just bounded by 2 plus little o of 1 times log Q. Before I go to the next slide, just to prevent some logical questions, so here in Murty's proof, there is an absolute value, and the null proofs there are also absolute value. You can expect that you may improve it a little bit if you remove the absolute value. And it seems that you actually don't get an improvement, at least by the tools that Kumar-Murty uses and by the tools that we use. So it's, we cannot do that. If we do it for the without an absolute value, we lose in one particular range. Okay. So let me first sketch a very basic and very simple part of the proof, because this is the least technical one. So this is the one for gamma Q plus. I'm going to focus for now just on gamma Q plus. So gamma Q plus is related to the logarithmic derivative of L. So I take the logarithmic derivative, I attach my lambda has a character, as always. Real part of S is greater or equal than 1, and we take any large x greater than 1 that we set up later, and we consider an approximation of this object, which we define as 1 over x, integral from 1 to x, of this finite now, well, the sum over n up to t, lambda of n over n, chi of n dt. So then my gamma Q plus can be written as gamma plus this sum. So I basically add this part, and then I subtract this part. So, and then basically what happens is that this part is small. So my main problem is now to deal with this part. So I'm summing all of this expression over Q between capital Q over 2 and Q. And then this one was studied by Kumar-Murty, because this one is a good approximation. So it kind of, you know, it becomes very small on average. So my real question is how to deal with this guy. Okay, so how to deal. This is yes. So now I need to know how to deal with this guy and keep track of the fact that I'm going to deal with this guy on average. I just don't write the average to make my formula shorter. So this is how it looks like. And here you can apply orthogonality for chi. And once we apply orthogonality for chi and we exchange it a little bit, it starts to look a bit like, you know, a sum with a bias. So we get here the sum over n that is equal plus minus 1 modulo q of lambda n over n minus the sum over n up to t such that n is coprime to q. So, and then my whole expression for the sum of phi is going to look like this. So the essential part is that I got from some question about logarithmic derivatives, I got to the question about the distribution of primes in arithmetic progressions, right? Because here I have lambda that detects prime powers. Here I get plus minus 1 modulo q. So I'm I'm now in my area, so to say, and I'm dealing with primes and arithmetic progressions. This is the essential part. Okay, so and now the remaining step, and I mean, the remaining steps, of course, they are ugly, but at least, like, at this point, you can see, at this point, you can see what you need to do. You need to determine the ranges where your classical good asymptotic, which is Ziegel-Walfish, applies. Then you need to determine when you can apply Bambieri-Vinogradov. You get the middle range. In the middle range, you do Barman-Halberstam or some sieving. So from here on, it's technical, but it's a pretty standard things, because this is the sum that we are working on. So, and we divide into convenient ranges, we apply Bambieri-Vinogradov, we use some sieving, and for R of Q, let me just emphasize the difference. For R of Q, we need the orthogonality, but for odd characters, because before we used orthogonality only for even characters. And if we just proceed in the same way, then my R of Q is going to be expressed like this. So here, I had lambda, which would give me logarithmic weights, right? Because I'm dealing now with gamma q plus. When I'm dealing with R of Q, I don't have logarithmic weights, but this is essentially the same expression. So, and I can study it by basically the same means. And this is the remark that I did before, that the same tools, they do not yield any improvement if you remove the absolute value because of one particular range where everything fails and you end up with trivial bound. Okay. So the most problematic one is cup of Q, because there you normalize by log. You see, here we don't have a log, here we have a log, and now we normalized it with a log, and we are in some sort of an annoying situation, so to say. Okay, so cup of Q, we can split it into easy contribution and not easy contribution. So Q minus 1 over 2 is just a factor that is before there. And then we have Q minus 1 over 2 VQ plus WQ. And VQ is some prime sum that is not so hard to deal with. And WQ is largest, is more complicated sum because it's related to the bias in here. So, and parallel, in the same way, you can do the decomposition for R of Q as well. And then similarly, in both cases, we can show that this term, VQ and TQ, they are bounded by an absolute constant divided by Q, so they're really harmless. They don't do any kind of mess. And we can even say something that they're equal to little of 1 over Q, except a small set. So we can even do something more precise about it. So, and this means that this part, WQ, and correspondingly GQ is the main object. So, and we are going to truncate it at some X. We are going to first use Brun-Titchmarsh in the head, in the first part of the truncation. And then we are going to bound the tail by the explicit formula and zero density result. So the first part is pretty classical. You choose the truncation, you use Brun-Titchmarsh, you figure out what range Brun-Titchmarsh is capable to provide to you. And so the main thing is really in bounding the tail and using the explicit formula and zero density. So let me talk a little bit more about it. So yeah, the prime power term is harmless. So this is basically the bound that we get for the prime power term. And then this means that everything lives in my capital sigma, which is related to W sub Q. So we fix L of Q to go to infinity, and we split into two regions, into the region when my P is less or equal than X1, where X1 is Q to the parallel of Q. P is between X1 and X2, so between Q to the L of Q and E to the Q, and P is greater or equal to than X2. In the first region, we apply Brun-Titchmarsh, optimize, and we are going to get log Q. I'm going to give more details, but this is just a scheme. In the second region, when we are middle primes, we are going to use explicit formula, and we are going to deal with Ziegel zero, and we are going to try to avoid the contribution of the Ziegel zero. Again, the usual tool. And the third range is negligible because there we can just use Ziegel-Walfish, because here the primes are greater than X2. Okay, so in the process, just let me specify that while we are doing that, we can actually improve all of our results a little bit if we make them conditional. So we can assume Riemann hypothesis, but only for odd characters. So let me just say what that is. If Q is an odd prime, then non-trivial zeros of Dirichlet series, here it should be just mod Q without a star. On the line, real part of S is 1/2. So if we assume this, then of course we can choose here, we can choose our ranges slightly differently here. And then we are going to get the improvement of the final results. So every time you automatically kind of follow the same way, and you get improvements assuming RH for odd Q. Okay. So in the first range, we are going to use Brun-Titchmarsh, and we are going to use this shape of Brun-Titchmarsh. So basically, we have this q minus 1/2 factor that was always there, 1/log, and then we have this sum, and applying Brun-Titchmarsh here, we are going to end up with this bounds, and then optimizing, we get this type of constant. So, and again, this can be improved if we assume Riemann hypothesis for odd character. Okay, so now talking about the connection to Ziegel zeros. For non-principal chi modulo q, if my t is between 2 and x, we have the following explicit formula. And then this means that for S2, for the second term, if we apply exactly the explicit formula, this is what we get. And there is a result about zero density by Lu and Zhang in 2008. And that allows us to bound the integral term by something that is log q divided by L of q, and L of q is going to infinity as q goes to infinity. So this is a nice term for us. So, and then we are using this nice and convenient formula, and we are going to end up with the bound for S2. Okay, so this we have done, and there is just some kind of optimization that needs to be done. How much? Okay, I don't have much time. So this is just some sort of optimization that we need to do for VQ in order to make our constants, like, more pleasant. And now let me just outline once again. Did I go? Yes. Let me outline once again that there is a very strong connection to the Ziegel zeros, and we are using that really a lot and really in a technical way. You can connect the difference between gamma q plus and gamma q with Ziegel zeros in the following way. So if k is not rationals, and dk is the absolute discriminant over the rational numbers, then the zeta k has at most 1 0 in the region in the complex plane. And if this zero exists, it must be real, and this is called a Ziegel zero. So, and Dixit and Murty in the same paper in 2023 showed that if zeta sub k has a Ziegel zero, then gamma k is equal to this object. And otherwise, gamma k is equal to big O of log dk. So then, if we just insert it, this means that the difference between gamma k plus and gamma k is equal to this, and delta sub k q is 1 if one of the odd Dirichlet functions of conductor q has a Ziegel zero and is 0 otherwise. So this means that the difference between gammas is really related to whether we have Ziegel zero or not. Okay, so and now if we do a little bit analysis of what it gives and what we can do for the normalized difference of my gammas. So then this means that if we fix any LQ tending to infinity with Q, then there are effectively computable constants Q0, possibly that depends on L, such that we have this bound. This is what we proved in a later paper. So it took quite a while to deal with that because the admissible sets there are not very pleasant. And again, in addition, if you assume Riemann hypothesis, then things get a lot better for this bound, but this follows the usual track because we use explicit formula there. Okay, and let me just tell you a little bit about what was known about the bounds on R of Q. So in 76, there was a first effective bound, which tells you that if h of q is equal to 1, the plus number, then q is small. And then there were multiple sharper ineffective estimates. And finally, in 2001, there was a result of this type, that the maximum between R of Q and 1 over R of Q is less or equal than a constant for a density 1 set of primes. And this can be made into 1 plus epsilon under Elliott-Halberstam. And we managed to improve all of these results in certain ranges. The theorem is a little bit long, so let me just state maybe the first 2 parts of it. So basically what we tell, so here, no, this is the wrong one, yes. So basically it improves here on the constant and on the behavior, because L of Q, again, this is a function that tends arbitrarily slow and monotonically to infinity as Q tends to infinity. So this gives you an improvement in the situation when we have like no Ziegel zero. And otherwise we get something like this, which works very precisely with the powers here. And the third part is that, again, the conditional result is the Riemann hypothesis holds, then we get this improvement. So this improves the previous result, but the ranges are slightly different. Okay, so I would like to finish with the remarks on the R of Q. So when we compare to the no Ziegel situation, if we assume Riemann hypothesis for odd characters, and we do believe that it holds, then it only allows to remove small factor. So it doesn't give us much, unfortunately. So it seems that it's not so strong here. And these constants that we get in there in the conditional situation, they can be a little bit improved if you are a little bit more careful, but not by much. So this is like the best we can see. So, and the good question is like how close this is to the truth if we believe whatever we want to believe. So Granville in the 90s speculated that this value is bounded by log q to the power 1/2 plus epsilon. So, and this result is being false if this power is being replaced by any smaller number. So this 1/2 is really related to a very extremely rare situation that no one believes in. So, and essentially what he says is that if we take an admissible set A, and this is the set of A1, blah, 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 AS, such that omega of P is less than P for all P, where omega counts the number of solutions to X times the product of AIX is equal to 0 modulo P, and we define the measure mu of A as the sum of the reciprocals, then we just can assume Hardy-Littlewood, the lower bound version. So we suppose that we have an admissible set, we choose B to be -1 + 1, then the number of integers and up to X such that the form n, A1, n plus B, blah, 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 AS, n plus B, all prime is of cardinality at least X divided by log X to the power S plus 1. So this is only the lower bound. And if we assume also Hardy-Littlewood for Fisher-Man primes, then we say that there are at least X over log square of X primes up to X such that 2P plus 1 is also prime. And then under these two conjectures, Granville showed that for every admissible A, both E of plus minus the measure of A over 2 are the limit points of R of Q. Because again, we are interested in the maximum of R of Q and 1 over R of Q. So in the full set of limits points is 0 infinity. So this implies that the Kummers conjecture about R of Q being like little of 1 is false under these two hypotheses. So it kind of, so we expect that the same kind of thing is going to happen to couple of Q. So if you assume these two, we can show that that here we have a similar result to Granville, and this means that the similar conjecture for couple of Q being equal to little of 1 also fails if you assume these two things. Okay, that's all I wanted to say, and thank you very much for your attention.
And Zoom? Anyone on Zoom?
Yeah, so I have a question. So as usual, the most interesting characters here are the real characters, right? So sometimes you can express the values of logarithmic derivatives in terms of some interesting algebraic numbers. So as far as I know, if you take a real character modulo Q and you take this logarithmic derivative, then this is closely related to some height of singular modulus, as far as I remember. So the question is, can we connect the values you discussed in your talk to some other interesting algebraic numbers?
Well, that's a good question. I didn't think about it, but I will need time to figure it out. No, we haven't tried. I don't say that it doesn't work, but yeah, we haven't tried that, yes.
So further, if I understand correctly, if you assume some form of ABC conjecture for ABC hypothesis for number fields, then you get some good bounds for logarithmic derivatives.
Yeah, this is right. Yeah, this we tried. It improves a little bit, but yes. But we have some other approaches that we think may overcome what we get on ABC. But this is in process, so to say. Yeah.
Okay. Thank you very much for your.
Thanks for your question.
Could you back up one slide?
One slide. Yes.
So, which of these three conjectures do you believe is false?
Well, the last one, I guess.
All right, let's thank Alisa again. And next talk as soon as we get set up. Thank you.
I'm not a good fortune teller.